Hello, my name is Luigi Manfretti, and I'm an associate professor at Rensselaer Polytechnic Institute. This talk is about deploying and calibrating power plant models in a cloud-based Synchrophasor platform. And the work is in a project with Dominion Energy. The list of contributors is shown on the bottom of the slide. Here is an overview of my presentation. First, I will start by reviewing Dominion Energy's needs for model calibration. After that, I will review some of the background of the advanced modeling and simulation technologies that make possible the cloud deployment. After that, I will present a small prototype that has been built, and I will conclude the presentation with some of the lessons from this exciting project. Before we start, on the right, we have a Proctusian bed. A Proctusian bed is an arbitrary standard to which exact conformity is forced. It comes from Greek mythology. Proctus used to chop the legs or pull the arms of his victims to make them fit on the exact size of the bed. What is the implication of this bed with modeling? Well, we must always be wary when attempting to force reality to fit a model, and we must always be prepared to develop and modify our models to represent new facts and observations. We cannot disregard phenomena that conflicts with the model, and even power systems world, also, we cannot disregard when software tools do not let us capture it. I bring up the Proctusian bed because this project has brought many challenges. In this picture, you can see a spectrogram for 24 hours of data at a generator unit. What you can see is that we have a great range of dynamics, from low frequencies that are persistent to dropping 10 Hz oscillations to 15 Hz. These are clearly in the measurement data, but the model shows none of them. 100 megawatts of this plant is tiny considering planning, and so they have been overlooked, but dynamics are important no matter where they rise. So this is one of Dominion's needs, to have models that better represent reality. They use the models in different tasks like many other utilities. Usually model calibration and validation requires events happening to capture data. However, ambient conditions, such as in this picture, are extremely rich and could also be leveraged. Existing models need to be updated to capture this on model dynamics, clearly. So the vision is to use a cloud-based data-assisted modeling approach using Modelica-based technologies. This will be deployed in Dominion's Synchrophasor cloud-based platform called Predictive Grid. Here, the idea is to create portable model modules for each of the power stations and apply advanced techniques such as linearization so that we can replicate these spectrograms. This will allow us to do quickly model validation and calibration on demand, either when you have events or during ambient conditions. And this should support planning and operation tasks. Here is a picture of Predictive Grid. It's an AWS-based cloud platform. It allows to ingest PMU data, store it, access it, and deploy your own applications. For cloud deployment, we have developer models using the Modelica language and the OpenIPSL library for power system modeling and simulation. Some of the facts about these technologies are described in this slide. Here is an example built using the Modelica language and the OpenIPSL library. You can see in this slide the power grid, the generator, and the excitation system. We can use both equation-based modeling, shown on the right-hand side, or block diagrams shown for the exciter. Having implemented the models in Modelica, it is possible to export them to be used in more than 100 simulation tools using the functional Mockup interface standard. This is an open access standard and is also open source from the Modelica Association. It defines a container and an interface to exchange dynamic models using a combination of XML files, binaries, or C source code in a single file. You can use the FMI standard both on model exchange or in co-simulation variants. In this work, we are using the co-simulation version. So, having explained the modeling and simulation technologies that we are going to use for this deployment, let me explain now what is the challenge. First, all of the models that are used by Dominion Energy and many other utilities is isolated. They're inside of PSSC. This limits the models to the capabilities of the tool. And unfortunately, because PSSC is a Windows-based application, it's impossible to deploy it in the predictive rig platform for many reasons. So the solution that we are using here is, with the new model and simulation technologies that I presented, we can actually make the models portable and deploy them in the cloud. However, the issue is that my library didn't have the exact models that Dominion needed. So the approach that we follow is the following. First, we implemented the models in a Modelica tool and we verified it against PSSC to give Dominion the confidence that we can give you the same or better results than PSSC. Next, if having the results being the same, we modify the model so that it can run in the platform as an FMU. Next, we deploy in the platform a tool chain for model calibration. First, we use Python functionalities to deploy the model, and next, we create a notebook that allows us to calibrate. There are different tasks in the model calibration process that I will present, but finally, the result should be that we are able to provide new parameters for the people using PSSC to update their models. After implementing each of the models that we needed in Modelica, we need to verify them. To conduct this verification, we set up unit test models. On the left-hand side, you see the PSSC model, and on the right-hand side, you see the model implemented in Modelica and using the OpenIPSL library. You can see that we have replicated the network topology, and now we have implemented all of the different components required for our model to run. This is one sample test that we perform. It's a three-phase fault to ground applied to the fault bus at time 2 for 0.15 seconds. We have simulated this model in two different Modelica tools. One is DIMOLA and the other one is Model on Impact. And we have used PSSC version 33. As you can see, we get a one-to-one match for all of the tools. We were able to reproduce exactly the PSSC behavior. To see more examples online of the verifications that we have done of our library, please go to the link shown on the slide. Now, we modify the models so that we can couple PMU data to do replay and to export it using the FMI standard and deploy it in the cloud platform. This requires us to remove the rest of the small test power grid and connect here through a voltage source, the PMU data being replayed, whereas the model will provide an output of the active and reactive power that we will use for calibrating it. Finally, at the top, we need to provide some data from a power flow solution that allows us to initialize the model. Now that the model is ready to be imported into the cloud platform, we need also to get some PMU measurement data. First, we need to retrieve the data. This is an example of the code that we use to do that in the notebook. Next, the data is prepared. So we need to filter it to remove very, very slow frequencies that the model cannot represent. We need to remove noise, and we need to resample the data to match the step size of the solver chosen. Finally, we need to define the signals for model coupling, and we need to calculate variables such as P and Q that are a product of the PMU measurements. Now that the model and the PMU data are ready to be used, we proceed to couple them. We will put together the model, the measurements, and an optimizer. For the optimization part, we use a tool called ModelSpy. After configuring the tool, we instantiate the FMU model, we define input and outputs, and we define the parameters to be estimated along with the optimization algorithm solution settings. With everything set up, we can now run a parameter estimation to attempt to calibrate the model to the data. We will calibrate the parameters Ka and Ta of the exciter, and we will also calibrate the steady-state active power and reactive power during ambient conditions. The optimization approach uses two methods. First, a genetic algorithm is used to find a global potential solution for the four parameters. Next, a conjugate gradient method is used to find and minimize the error. Finally, the error is shown in the last plot, where you see how the generic algorithm is operating first, and second, the Nedler-Mead algorithm is being executed. The total time elapsed was 1,431 seconds to perform the optimization. Here are some interesting results. Following the same approach, we calibrated for a transient event. Here are the results of comparing the simulation to the data for both ambient conditions and transient event. We found that the gain parameter Ka kept a value of the same order of magnitude, whereas the parameter Ta had several orders of magnitude of difference. One of the things that we believe is that the current parameters being used do not represent dynamics accurately. So, for example, you see here the damped response versus the undamped response from the simulation. So, we obviously need to include more parameters and parts for the model, parameters such as the stabilizer and of the turbine governor. In addition, we might need to revisit if the component models used are the right ones, because as we have seen in the data, many parameters are not even used and the modelers don't know why. We need also to analyze this under many scenarios, not just a transient event or ambient conditions, but also, for example, set point changes. Well, this is not the only thing that we need, but we also need means of doing uncertainty quantification and sensitivity analysis to know how to proceed in a parameter calibration. What have we learned in our project? We have learned that open access, meaning no paywall, standards-based, portable and reusable modeling using Modelica and FMI allows us for model portability. And this allows us to have models we can use in multiple environments and for multiple tasks. These standards provide great benefit for integration in many platforms, as in our example with the cloud. This also makes very flexible to move around our models without a specific tool dependency. With regards to working with a cloud-based Synchrophasor platform, the availability of Python tools allowed us to quickly develop a prototype. Custom Python routines to process our data so that we can do model validation were implemented also without too much of a hassle. Finally, the new prototype allowed to identify features and enhancements and new functionalities that the platform will need to facilitate for this kind of applications. For example, we need bigger AWS instances to run our optimizations within a reasonable amount of time. The proof of concept seems to be successfully implemented. The results show great promise for automation of model calibration within a Synchrophasor utility platform. It gives also a framework that can be generalized for any other kind of generator stations, fax devices, renewable energy sources, and so on. Open source tools definitely made the development effort easier, both on the modeling side, but also for the optimization side. We need to develop some methods that allows us to perform better parameter selection and correlation analysis, such as sensitivity and uncertainty quantification tools. In future work, we plan to enhance the prototype and expand coverage to other stations of the energy and to use the models in new applications. Thank you very much for your attention and for inviting me to this panel.